Welcome to the first episode of Facts in Mind with Kimia and Amber. Today on Facts in Mind, we're thrilled to be joined by Dr. Max Krasnow, a leading evolutionary psychologist and faculty member at Harvard University. His research focuses on evolutionary foundations of human mind, how natural selection has shaped the way we think, make decisions, and navigate complex social environments.
Dr. Krasnow's work bridges psychology, cognitive science, and evolutionary theory to better understand the architecture of human reasoning. And he brings a uniquely insightful perspective to today's topic. Do AI models like ChatGPT really understand us?
Welcome, Dr. Krasnow. We're so excited to have you here. Thank you for being our first guest. We have some questions for you, and I was very excited to hear that you gave a talk on this at Harvard University. So thank you. It's an honor to speak to you about this here as well.
Thank you so much for having me. It's a pleasure to be here. It's an honor to be part of your first episode. I'm looking forward to it.
Dr. Krasnow, to kick things off, what does it actually mean to understand something? How do scientists or psychologists define understanding in the brain?
That's a really good question, Amber. The concept of understanding is something that I think we all intuitively have a notion of. But when we try to get very specific about it, it becomes hard to draw really bright lines. One kind of classic example that helps think through what we might mean is the Chinese room thought experiment. Roughly, it goes like this. Imagine that there was a person in a room, and what they had was an amazing dictionary, essentially. And in that dictionary, they had a list of every single possible sentence in English and Chinese and the mapping between one and the other. Outside the room, what you could do as a person is take an English sentence, slip it through a slot, and the person inside the room would make that translation using their book and write it on a piece of paper and send it back out to you. From outside the room, it would look like what you had was somebody who understood both English and Chinese because you're getting those perfect translations. But would we consider that person to actually understand English and Chinese? Probably not. That doesn't usually rise to the level of what we mean by understanding. This seems more like a lookup table, something that you could say, this equals that, with a whole long list of those things. That doesn't really feel like what we mean when we say that a human understands something. Now, if we were to go steps further than that, it does get more squishy. One simple way to think about what understanding might mean that's closer to our intuitive notion is to have a representation of some structure of information such that you're able to draw inferences from it and have those inferences be accurate. So let's say you wanted to know if a child had an understanding of other people having their own minds that had access to their own information and not necessarily all of the information that the child themselves had access to. In developmental psychology, this is often referred to as theory of mind. The way that you test for that kind of understanding is to see if the child is successfully able to make predictions about other individuals that have their own minds but have different information from the child. And so in this way, I think we can see that a definition closer to that human notion of understanding is to have some sort of structured representation of information that you can then take that and infer new things from.
So AI like ChatGPT talk in a way that sound really smart and human. Why do you think that is?
That is essentially the way that the model is set up. It's exactly what it was designed to do. The way that these models work is that they started out with a large training data set. companies like OpenAI, when they were training ChatGPT, started with millions and millions of records of human speech. And what the model did then was looked for associations between words that were common, looked for associations between phrases that were common. And the way that it's trained is that it tries to predict what words would follow other words, and it would get rewarded. So a process or an association would become more likely if it made a successful association, if it was successfully able to predict that next word, and it would be punished in a sense. It would loosen an association, remove an association when it's unsuccessful at predicting what word might follow some other word. So essentially, you have a model that became better and better and better at starting at the beginning of a human sentence and then predicting the next words in that human sentence. And once you have a model that can do that, you can essentially have it start its own sentences as responses to prompts. And so it can basically create sentences that mimic the structure of what a human would say in response to a question. Now, what that means is that this model is putting on the act of being human. It's not generating those sentences the way that we generate sentences. It's not looking at meaning and taking meaning and translating it into words. It's starting with word associations and then stringing those word associations together in order based on what the most likely next word is going to be. That's roughly how it works. Now, what you then have is a model that mimics humans very well. And when people hear or read text that sounds like it was written by a person, it's very easy for us to imagine the mind behind those words.
So, why do you think our brains are so quick to treat anything that talks like a person, like a chatbot, as if it is the real person? Is that something built into us over time?
I think that is essentially correct. We can see lots of examples in our everyday lives where we over attribute agency. That's the more kind of within academia way of saying it, where we assume minds where they don't exist. One common example you might have seen kind of circulating around the internet is this phenomenon of, I think it's pronounced pareidolia, where you see faces in everyday objects. A particular arrangement in a doorknob might look like a face. You slice a bell pepper, and based on the way that it grew, you might see a face there, and it might show an expression, and you might get a sense of how it feels. Even though you know that that pepper doesn't have a mind, and you know that it doesn't have a face, and you know that it doesn't have an emotional expression, we have a very strong impulse to infer those things based on that visual stimulus. The question then that you followed with is why? Why would we have this tendency? This gets back to an idea that was proposed several decades ago by Hazelton and Buss. The idea is called error management theory. There are essentially, when you're perceiving the world and you have to make the choice of whether treating something as an object that doesn't have a mind or an agent that does have a mind, there are four possible outcomes. You can correctly identify that it's an object. You could correctly identify that it's an agent. You could treat an object like an agent, or you could treat an agent like an object. What error management theory does is it asks us to compare the cost of those two errors. And it then predicts that a naturally evolved system, an optimal system, will trade off in the favor of making the less costly error. So if you treat a bell pepper as if it has a mind, it's not going to change its behavior. You might look a little silly, right? It's not going to lead to any potential harm. But treating an agent like an object, that could actually lead to some real risks. If that twig snapping behind you is a predator lurking and about to spring on you, not treating it like a predator could get you killed. If there's a person who means you harm and you don't recognize them as a person, you can't take action to prevent that harm. Or if there's a person who wants to help you and you don't treat them like a person, that's help that you're not going to get. So because the costs of those two errors are so asymmetric, we have a psychology that is biased towards taking very sparse information about whether or not something could be an agent that has a mind associated with it, and biases in the direction of assuming that it's an agent.
For our listeners that might not be too familiar with evolutionary psychology, I was wondering if you can explain a little bit about cost, trade-off, and there was one more that you said, which I think they are very common words, especially for evolutionary psychology. But if you can just give a little bit of background so that it's easier or they become familiar with the terms.
Maybe it'll help to give a modern day example of a machine that's designed on the basis of this error management approach. We're all probably familiar with car alarms that go off for apparently no reason. In fact, vastly more often is a car alarm having a false alarm than it is actually responding to an attempted break-in. Why is the system so sensitive? It's sensitive because it can't know for sure whether a particular sensation that the mechanism is picking up is a break-in or not. It's taking that information and making an inference. It has to have a threshold of if it has enough evidence, it's going to make its alarm. If it doesn't have enough evidence, it's not going to alarm. Now, if it has a false alarm, if it goes off when there's nothing happening, it creates some minor annoyance for everyone around. But if there actually is a thief trying to steal that car and the alarm doesn't go off, that is a much bigger cost for the car owner. So if you were an alarm maker who doesn't want to be selling systems that don't detect theft, or the car owner who really doesn't want their car stolen, you would much prefer that system to be very, very sensitive and make many more of the cheap error, false alarm, than the expensive error, missing out on that actually being an attempted theft. We can map this to that same circumstance in agency detection. Which one is worse? Thinking that a pepper has an actual emotion, thinking that a person isn't a person. There's lots of reasons to suspect that that latter error, failing to pick up on an agent's mind, is going to be much worse to do. And therefore, a system that has been optimizing that psychology over time is expected to bias the system so that it's likely to make that error less often.
As continuing on the same topic, do you think our social instincts, like, being able to guess what someone else is thinking, makes us more likely to believe AI has feelings or thoughts even when it doesn't?
I think that's absolutely true. We are an incredibly social species. If you look at the kinds of relationships that we have, We have relationships that no other animal is able to build. We have friendships of all kinds of degrees of closeness. We have work relationships. We participate in sports teams. We have state affiliations where we work together as a tax-paying group. Same with our nation. We have armies that work together. We have churches and synagogues and mosques. We have families and we have extended families. There are so many overlapping social groups that we behave in so flexibly and fluently we don't even notice how complicated that would be for a foreign organism to actually do. If we look across species, we can see how hard it is because no other species is able to do it. Now, a big reason why we have the ability to do these things is because there's so much good that we can have access to through social relationships. By building friendships, you have someone who can help take care of you when you're not doing so well, someone that you can rely on. Um, by building these family connections, you have other people around who can help you out and you can help them out in return. By working together as a team, you're able to do things together that you're not able to do individually. Now, if you think about the other people in your life, imagine that you're experiencing an emotion. You're angry because something happened to you. If the other person wasn't really picking up on your feeling, even though you keep giving them signals that you're having that emotion, that probably wouldn't feel very good, right? You might not think that they care about you that much. You might not think that they get you really, and that's not someone you necessarily want to remain close to. Being able to be on the same wavelength as someone else is a good sign that that's a relationship that you want to build stronger into the future. Being able to detect each other's emotions make social relationships happen more smoothly. And so we have a lot of ability to be able to read emotions on other people's faces, hear emotion in their voice, and to make those inferences quickly on the basis of just a small amount of information. And again, this is an error management situation. Failing to pick up on someone's extreme emotion is a big problem. Assuming that someone's angry when they're not such a big deal.
Let's jump over or just to highlight voice and that inference. Do you think our brains are wired specifically to trust fluent, confident speech? Because it sounds like someone who knows what they're talking about in the case of the AI.
I think that's absolutely right. There's actually some work showing, all the way back with very young children, toddlers, that they pick up on the fact just by observing someone whether or not they seem to have competence, like whether they seem to choose the right tool for the right job, use a tool effectively. They're able to figure out who has competence, and then they preferentially choose those competent people to learn new information from. We're basically built, even from very young ages, to not consider everybody in our world to be equally trustworthy, not everyone in our world to be equally knowledgeable, but we use cues like, are they effective in their behavior? Are they using big words that someone could only use if they know those words? Are they doing things that appear skillful? To the extent that they are and doing it successfully, that suggests that they have that level of competence. So when you have an AI that is so well trained to mimic fluent human speech, it's easy to see why that would give the impression that there's a competent, knowledgeable mind behind the creator of those sentences.
Well, with all this information you're presenting, I think the big question's now becoming, what's the biggest thing people may be getting wrong about how AI is working?
This is something that I think about a lot. When we compare the human mind to these AIs, we see that they work very differently. What the AI is designed to do, particularly when we're talking about a large language model like ChatGPT, which is one of a larger class of models called generative AI, these models are trained, designed to produce a particular kind of narrow output. That's fine. But if you look at what humans do, we do millions of things. Not only do we speak fluently in whatever our native language is, but we also can ride a bike sometimes. We can also ride a skateboard sometimes. We can also paint pictures sometimes. We can also do all kinds of other things. The reason we have this flexible ability to do so many things is because we have many, many, many mechanisms in our brain designed to tackle specific, smaller pieces of those problems. We have mechanisms in the visual areas of our brain that aren't there to look at the entire picture and see everything in every way, but rather to do very specific sub-pieces of the vision problem. Just pick out the edges around objects. Put those edges together into shapes, right? Specific sub-pieces of the visual problem then allow you to put those things together in such a way that you can recognize an object, make an inference about how big it is, how far away it is, what's it made of. This is very different than the way, for example, that a camera works. Cameras aren't using lots and lots of mechanisms to detect lots and lots of different kinds of information to put it together. Cameras are taking an image of light levels across an array, across a two-dimensional space. And when we see that, our brains can then parse that up into, oh, that's my Aunt Jan. This is her dog. This is their house. I can tell that Jan was not feeling very well that day. Her dog's looking kind of old. We can see so many things in a picture. That camera is not seeing all those things in that picture, right? It's representing the image in a way, but it's not representing it the way that we do, and it's not able to do the things with that image that we are. It's the same thing with these generative models. They're creating these sentences, and it looks good. They look like fluent sentences created by a human mind, but they're not. They're not understanding that content in the way that would allow them to do all kinds of things with that information, right? And because they don't have that level of understanding, they don't have the chance even of being what most people think of when they think about AI. When people think about AI, they imagine something like the Terminator, right? They imagine Skynet. They imagine some kind of system that isn't just doing one specific limited thing, but doing everything, right? It can work just like a human to get somebody speaking to it, and then it can talk back, but it can also control everything in your house, and it can plan for the future, and it can make decisions about what's better, who would prefer what are they likely to do, anticipate what their needs are, all kinds of things. A model that's just predicting what the next couple words are in a natural human sentence, that doesn't even come close to the number of specific modules that you would need to work together to create something like human level general intelligence. Something that actually would be like those science fiction AIs, like the Terminator or Skynet. So if I had to pick one thing that people get most wrong, that probably has the biggest impact on how we treat these models and think about them, is using the fact that these models can speak relatively fluently to use that information to infer that they have something like general intelligence. Just because they're representing human language and able to predict human language a couple words at a time doesn't mean that they have that level of understanding that's going to allow them to do all those kinds of things that a human would do with that information.
So seems like from what we've been hearing and maybe also been reading about AI, seems like something's still missing. How close are AI models like ChatGPT to really thinking like humans? And what are the big pieces they're missing still?
That, I think, is the billion-dollar question. I think it is possible to design a machine that can think like humans. And the reason why I say that's possible is because humans exist. There actually is such a thing as a human brain, and it does actually do all the things that humans do. Our task is to reach that level. Well, not our task. The task for someone who's trying to do that with AI is to mimic that machine or its functions well enough that it can actually recreate that design. Now, this gets us then back to the fundamental differences between our existing models and the way that the human mind works. Our existing models are narrowly tailored to take a wide variety of linguistic prompts and generate sentences in response to those prompts, or generate an image in response to those prompts. We have specific models that are getting better and better at those specific tasks. But what we don't see is how information is going to have to be pulled together in the correct way across specific models that are designed to do different things, that it's only when you can have a collection of those things that has a large enough set of the right kinds of mechanisms that are put together in the right kind of way before you're going to get anything like a general intelligence, let alone one that approaches the level of human cognition.
Some people say AI is just copying patterns it's seen before, but humans use patterns too. So what's the difference in how we do it compared to AI?
Yeah, that is an interesting question. I think what it might come down to is two mechanisms can see the same thing and get different information out of it. There's a somewhat classic experiment in psychology where you give people the positions of chess pieces on a board, and their task is to memorize the position of those pieces. Even talking about two humans doing that task, you can get vastly different performance because those people are coming at that problem in vastly different ways. A chess novice doesn't recognize the pattern as having any meaning within the context of a game of chess, and they have to pay attention to each individual piece. They tend to not be able to memorize entire chessboards very well. Chess masters who are able to look at that same amount of information that objectively is existing in what they're seeing, and they're able to pull out an inference about it. They're able to see a certain thing in it that compresses the information enough that they're able to capture the entire position set on the board and in fact do multiple of those. They're able to remember multiple chessboards because they can recognize it as a particular arrangement that you would get if two people had played it to this outcome. It might even have a special name. We can see the way that these generative language models work. They take the words that you write to them in a prompt and they break it down into individual words. They break it down into what are called tokens, which are sometimes collections of words. And they essentially assign that a number and they plug that into their model to predict what those next words will be. That's not the way that we use language. It's not the way that our brains treat sentences. Let me give you an example. If I asked you, what time is it, in the context that we have now, you would probably look at the clock on your computer or the watch that you have on your wrist and just tell me the time. But if we were at a party and you knew that I'm not a very social person, I don't like to be out at parties, and I came up to you and said, what time is it? You might infer from that that I was feeling like I had been there long enough and I would like to go. Now, that inference is not going to be made by ChatGPT, right? ChatGPT is not going to be able to be sensitive to those kinds of pragmatics in a circumstance. The way that our brains work is that we're able to take all of this information that comes from so many different sources. We're able to put it together to understand in a very sophisticated way what is the information that we should be attending to. What is that stimulus, that signal? What is it actually communicating? That is just leagues beyond the information that ChatGPT is pulling out of a sentence and the way that it's producing language.
Really interesting. It's very thought-provoking. So based on what you said, what I understood is that it is possible for ChatGPT to get there. It's just not there now because you need to plug in so much information, which as humans we've picked up, from all these different senses and different things that we've experienced through life. That's how we have made these different like inferences. We know the difference between, like if somebody asks you what time it is, the setting is going to make a difference. So if ChatGPT had that amount of information to, build it, then maybe eventually it can get there. But right now, we're nowhere close to that. Is that true? Is that what that meant?
So I think that that is true to a certain degree. If we could recreate the human brain in silicon or in um, programming, we would be able to have a machine that did what we do.
Mhm.
The approach of AI companies like OpenAI or Meta, Gemini, whatever, the approach that they're taking is they're starting out with a model and allowing the world to tell it what it should know. It's using the experience of lots and lots of training data to be able to pick up on statistical associations in that training data. Now, if there was everything objectively there in that training data that would allow them to pick it up, then it might be possible for that strategy to be successful. The problem is that that's not how we come to behave the way that we do. And it's not even possible in principle to arrive at a human-like representation from that kind of training. There's a thought experiment in philosophy that I think illustrates this nicely. It's called the Gavagai problem. Imagine that you were an astronaut that landed on an alien planet. And when you got there, a little alien came up to you and pointed off in a direction and said the word Gavagai. Now you follow their point and you see that they're pointing at what looks to your eyes like a plant. What should you infer from that information? We're very tempted to respond, well, it's obvious. They're referring to that thing as a gavagai. That's what that plant is. In fact, it's not the name of that plant, it's the name of that plant species. If we saw something else that looked like that, it would also be a gavagai. However, that's not the only possible thing that that might mean, right? The alien could be pointing and saying, that's dangerous. The alien can be pointing and saying, that's the gavagai color. The alien could be pointing and saying, this is my pet gavagai. And that individual thing's name is gavagai. In fact, there's an infinite number of possible things that any piece of information could mean. There has to be some pre-specification of the hypotheses that you're going to form in advance, some pre-specified narrow set of inferences that you're going to make from any piece of information for you to actually learn anything. The incredible power of the human mind is that we have lots of those pre-specifications built in. For example, we have that pre-specification that when we hear something like that alien pointing and saying the word gavagai, we interpret it as naming. We interpret it as naming a category, not other information about the thing and not specific information about that specific individual. That's a very useful pre-specification to have. That's actually a very efficient way of learning words. So if we both use that when we're teaching people things, and we use that when we're learning from others, that's going to be a very efficient way of transmitting a language from one generation to the next. But without having that built into the system, without having that constraint built into the system in advance, no matter how big the model is, how powerful, no matter how much training data it has, it's never going to be able to test all of the infinite hypotheses for all of the infinite pieces of information it has, or very large number of pieces of information that it has, to be able to recreate a human mind's worth of knowledge. Trying to tie this back into how the question started. Now, we can see these constraints and this pre-specified information all throughout our brains. We can look at an object and just from the experience of seeing the front of it, make inferences about what the rest of the object looks like, right? We can infer that it's, from the facts that I'm holding it, you're inferring that it's light enough to hold. From the fact that I'm pinching it like this, you're inferring that it has that same shape all along the back. Because objects tend to be a consistent color unless there's a good reason for them not to be, you're going to infer that it's also purple on the back. Our brains make all kinds of assumptions when we see information. And those assumptions work. They work because they've picked up on true things about the world that have been true for millions, if not billions of years. Now, these models could potentially have all that training data, but the question is, are we going to be building the model in such a way that it can pick up on what it should be picking up on? And I think that's going to be a real challenge if we're going to get anything approximating a general intelligence.
Thank you. That was really helpful.
So, now that we're sort of really understanding, where AI is at this moment, um, and we're also noticing AI is showing up now in schools, therapy, customer service, even mental health apps. Do you think there's a risk in how quickly it's being used, especially if people don't fully understand or get how it's working?
I think there absolutely is a risk. And I think that we are seeing the evidence of that risk every day. We are seeing these AI models getting pushed out into apps that people can talk to. And we're seeing them say things that the designers of the app never imagined that they would say, but that lead to terrible outcomes. There have been cases of, teenagers interacting with virtual friends, virtual romantic partners through an AI app, and having those experiences leading them to commit suicide. We have AI models that have convinced people to give up their other real life relationships because they're finding this particular relationship so valuable. We are having AI models that happily create illegal content. For example, uh, creating sexualized scenarios involving minors, even though the designers of those systems didn't intend for that to happen and tried to prevent that from happening.
Mm.
The problem is, because these models don't actually understand, we can't trust them to understand enough to behave well. When we put them in circumstances where they're interacting with particularly vulnerable populations, children, people with mental health challenges, etc., we need to be much more cautious than we're being, that we're putting guardrails on what we're expecting the model to do, what we're allowing the model to do, and what level of human observation we're giving to what the model does.
So now that we're really understanding what the AI model can do in this moment, what can scientists and educators do to help the public better understand AI without either scaring people or overhyping it?
I think that the best thing that educators can do is to engage with their students with AI, to actually proactively address the fact that students are going to be using it. And I think one of the first lessons that people need to see, students in particular, is that AI is fallible, that AI makes mistakes. It makes silly mistakes that humans don't make or that humans wouldn't make. I actually do this kind of activity in some of my own classes where I have students take the problem that they've been trying to solve all semester and plug it into their AI model of choice. Now, when you ask the AI, how would you solve this problem? The first response that it gives you almost always sounds pretty good. But AI tends to be vaguer than we think at first glance. I have students not just take that first response as the final answer. I want them to, I ask them to keep asking the AI, how would you do that? until they feel they have a level of detail and explanation that they could actually follow that plan out in the real world. Everyone has found that the AI has not been able to meet that challenge. The AI is able to string together words that repeat the statistical relationships of common patterns in the world. But what that has created is a relatively vague sentence that, when you're looking for concrete detail, tends to fall short. And when you keep asking it for follow-up information with more concrete detail, it falls farther and farther away from an answer that you can actually use. This, I think, is the kind of activity that would be very helpful for educators to do in their classrooms. Because if students can see how fallible these models are, they won't trust them as much and won't let them replace their own thinking for their own work.
For the closing thought, what does a healthy interaction with AI look like? Psychologically healthy.
I think the way that people should relate to AI is the way that we relate to other kinds of tools that we use. Let me give you an example. Before the pocket calculator was invented, when people needed to multiply large numbers, they used something called a slide rule, mechanical device for computing products. When the digital pocket calculator became popular, there was a lot of controversy over whether these should be allowed in schools. People saw using a slide rule as an important skill for people to have, or they thought that using a slide rule somehow was important for developing an understanding of mathematics. Turns out neither of those things are really true, because the slide rule isn't a thinking device. It's something that a person uses to solve a problem. And you can substitute a digital calculator as a more efficient tool for solving that same problem. But the calculator isn't doing your thinking for you. It's a tool that your human mind is using, right? You couldn't take a word problem and put that into the calculator and just trust the output, right? That calculator isn't designed to do that. In fact, sometimes you can give humans word problems, and we can have a hard time understanding what question is even being asked. Sometimes people can hit the wrong button on a calculator. If you accepted that answer as the right answer, you could be in trouble. But we don't always necessarily just trust what the calculator says, right? If you were adding up a bill, so you're computing down, the items that you're going out shopping for to see if you're within your budget for that shopping trip. If you got to an answer of what that was going to be, and it was like something like $1 billion, you wouldn't just take that as the correct answer, right? You would assume that something went wrong with your process. You can only do that because you're not letting the calculator do the thinking for you. You're just using it as a tool for a specific purpose. We should use AI the same way. AI is very good at doing particular things, but it's not good at thinking the way that human minds think. A healthy relationship with AI is one that uses it as a tool and sees it as something that can produce great information, could produce false information, but something that we need to check with our own human minds.
Thank you, Dr. Krasnow, for being here and speaking on this fascinating topic. Thank you to our listeners for joining us for this episode. And I want to also thank Amber because she's put a lot of work in making everything happen this week, from the marketing side to our website. So thank you, Amber. Facts in Mind is a podcast for curious minds. We explore everything from science, psychology, and technology to education, culture, and public health. Be sure to follow and subscribe so you don't miss on exciting episodes with the latest thoughts and research from our expert guests. Thank you again, Dr. Krasnow.
Thanks for having me.
Thank you very much, Dr. Krasnow. This was super helpful.